Do you know why latches are important in various sectors of VLSI design and verification? Do you know how SystemVerilog differs in latch creation with respect to Verilog? Do you know how crucial is the verification aspect of always latch construct? If asked in interview, can you differentiate among the three mutually exclusive always constructs introduced in SystemVerilog? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In this episode, we will explore why always latch is introduced in SystemVerilog. In Verilog, the traditional always block is used for modeling both combinational and sequential logic. However, unintentional latch inference was a common issue, often leading to unintended circuit behavior and making debugging difficult. To address this, SystemVerilog introduced the always latch construct. The specialized block explicitly indicates the designer's intent to infer a latch when a variable is conditionally assigned but lacks an explicit default value. By using always latch, synthesis tool and simulators can detect incorrect and unintended latch inference more effectively, improving code clarity and reducing design errors. These enhancements align with the SystemVerilog's goal of making hardware description more predictable and maintainable at the same time, while minimizing unintended synthesis mismatches. Before going any further, I'd like to emphasize that in our Verilog series, we have an episode which is numbered as episode 5, and there we have talked about the always block. In case you have forgotten or you are not familiar with the always block, please go ahead, watch this episode from the Verilog playlist, or alternatively you can access this episode directly from the link provided in this video description. So without any further delay, let's begin today's episode. So in this episode, we will explore the below topics. First, we will talk about why always latch introduced in SystemVerilog. We will go in depth. Next, we will talk about why latches are crucial in VLSI. That means we are talking about the entire VLSI design, anywhere and everywhere of the VLSI design, why these latches are crucial either for designing, that is we intend it to be there, or unwanted latches, that means both sides, where we need and where we don't need. All the landscape will be covered. Next, we will go to the methods of latch detection. Here we will generalize and talk about the detection methods of latch. That means we will talk about if there is an unintended latch. That means a latch is coming into your design which you have not intended by your RTL code. Or maybe it could be an analog design. Then also we have methods to detect latches through different SPICE tools. So this is in general spread over the entire landscape of digital and analog. So we'll talk about the general methods for latch detection across multiple areas of the VLSI design. Next, with and without always latch. So we will explore the scenarios, that means the cases where we have used the always latch and where we are not using the always latch. So we will talk about to make things clear for you. Next, we will go for the verification aspect of the always latch. Here, the SystemVerilog used for designing both hardware as well as for verification. That means the always latch, when it is used in SystemVerilog for anything, how it will impact the verification. That means the digital verification. We will talk in detail about that. At the last, we will compare the three things, that is always FF, always COM and always latch. Always latch we are discussing in today's episode, and these two we have discussed in the last episode. So here we will compare all the three sisters side by side and we will make a conclusive idea. That means you can say some sort of key points to remember for you why there are three instead of a single always that was already existing in Verilog. Here we will conclude this episode and that's the menu for today. So without any further delay, let's move on. Now in this slide we will talk about why always latch is introduced in SystemVerilog. Here goes our explanation in this box. The always latch construct in SystemVerilog, that is SV, was introduced to enhance code clarity and reduce bugs by explicitly defining intent when modeling level sensitive, that is latched based behavior. It ensures that block is specifically intended for latch implementation and will generate a compiler warning or error if conditions are not met to synthesize latches. That means the always latch is there to create a latch properly, and as per our RTL instruction, if the latch is not created, it will flag some message. Reason why we have the always latch in SV. First, intent clarity clearly indicates the purpose of creating latches. So here our design intent, that means our intentions are to create latches, and it clearly depicts that. Error prevention. This helps designers to catch unintended latch inference due to incomplete sensitivity list or conditional statements. So in previous episode, we have seen about the latches getting created due to some sort of coding mistake like the sensitivity list or the missing else. So these are mistakes, and a human when designing the RTL can make mistakes. It could be a keyboard typo or something logic that was not clear. However, we must have set of measures to rectify that, and always latch is that measure, and hence it will do the error prevention. Next, we have debugging ease, makes it easier to locate and debug latch related issues. That means when we are debugging a scenario, when we are verifying or we are synthesizing and we came across that there is a latch which should not be there, we have to investigate that, and in advance the always latch helps at that point. That means in case you have some sort of mistakes that is creating a latch and which is not intended and it should not be there, always latch gives you a message. As well as if you intend a latch to be there and it is not created, in that case also it will give you a message. So your debugging is now much more easier as compared to the Verilog. Code readability enhances maintainability by explicitly differentiating latch-based logic from combinational sequential blocks. So this particular always latch block creates a separation from the combinational and sequential block. So latch is latch, and that is covered only and only by always latch. In digital design, clarity and correctness are crucial, especially when dealing with storage elements like latches. SystemVerilog introduced always latch to address common issues that arise with traditional always block by explicitly indicating that a latch is being inferred. It helps designers avoid accidental latch creation due to incomplete conditions or sensitivity lists. This is not only reduces unintended behavior but also makes debugging easier by clearly marking latch related logic in the code. Additionally, it improves readability, making it easier to distinguish between latch-based, combinational, and sequential logic. Ultimately, always latch enhances code maintainability and help prevent synthesis mismatches, leading to more reliable hardware designs. We are done with this particular slide, so let's move on. Here in this slide and two upcoming slides, we will discuss about why latches are crucial in VLSI. When we say VLSI, that means not only in digital design, we cover the entire landscape. Latches play a crucial role in VLSI design by providing temporary data storage and ensuring proper data flow within circuit. Unlike flip-flops, which operate on clock edges, latches are level sensitive, making them helpful for low power and high speed applications where minimal clocking overhead is needed. They help in reducing timing bottlenecks, optimizing power consumption, and enabling efficient data transfer between different clock domains. While they must be carefully managed to avoid timing hazards, latches are essential for designing energy efficient and high performance integrated circuits in modern VLSI systems. Now let's dive in for details. Preventing timing issues. Latch induced hold time violation. Latches are level sensitive devices and improper use can cause timing problems like hold time violation. This occurs when a signal arrives too early at a latch, causing incorrect data propagation. We already have a series on the static timing analysis, and also we do have the marathon of the same, split into 4 episodes. That means the marathon has 4 episodes. You can go over to the marathon playlist, or you can go over to the static timing analysis playlist to get the details of hold time violation, what is hold time violation, and how they are practically resolved. Because we have used open timer, so we have a marathon episode where we have given all the examples of open timer. So from there you can also check this setup and hold violation related test cases. So please go ahead and watch that in case you have a thirst for knowledge of what is the hold time violation. Now let's come back to our discussion. Clock domain crossing. In designs with multiple clock domains, undetected latches can result in metastability or data corruption. So this is another risk. We also have a clock series, that means clock tree synthesis, etc. in our channel. In case you want to have knowledge on that, please go ahead and watch that series from the playlist page. Next is avoiding race conditions. Latches are level sensitive to the duration of the clock level, that is high or low. If not properly designed or detected, they can introduce race conditions where the data changes unpredictably due to simultaneous operations. So this is why the latch is very much crucial. So it has to be carefully designed, placed and used. Number 3 is improving functional correctness. Transparent behavior. Latches can unintentionally become transparent when enabled, causing unintended data overwrites or losses. Detecting these scenarios ensures that the circuit performs as intended. So there could be lot of cases. That means these cases could be positive, it could be negative, it could be intended, it could be unintended, and we are exploring all of them. In the next slide, we'll go further and know different more scenarios. We are in the next slide, and let me display the box. Here, the next point is minimizing power and area overheads. Power consumption. Undetected latches can lead to unnecessary switching activity, increasing dynamic power consumption. So this is a power related issue connected with the latch. Area inefficiencies. Latches may require additional logic for proper operation, leading to suboptimal area use. Early detection helps streamlining the design. Now, already we have an episode on PPA, that is power, performance and area. How these are optimized in VLSI and why these are very important in VLSI, we have discussed in the PPA episode of FAQ playlist. So please go ahead and watch that episode. And the direct link of this PPA episode is given in the description of this video. Now, the next point is simplifying static timing analysis, that is STA. Latches complicates STA because their level sensitive nature introduces timing dependencies that are harder to analyze compared to edge triggered flip-flops. Detecting latches ensure that timing paths are correctly modeled and validated. Again, I am saying we already have a playlist of STA and also we have marathons. In case you do not have the basic knowledge of STA, please go ahead and watch those marathon or episodes from the STA playlist to understand in detail. So here also we have discussed PPA and STA related concerns of the latches in VLSI. Now let's move on to the third and final page about the latches cruciality in VLSI in the next slide. Enabling robust design flows. Modern VLSI design methodologies aim to identify and flag potential issues early in the design cycle. Latch detection facilitates design rule checks, that is DRCs, design for testability and fault tolerance mechanisms, improving the overall robustness of the design. So here we have already talked about the DRC in a FAQ episode. In case you want to have some knowledge, you can go ahead and find it from the FAQ playlist. We don't have yet the DFT related episodes yet, so you have to wait for them. In a general or a nutshell, I can say that these are the things that actually minimizes the issues with the design and hence risk mitigation before the actual fabrication. And hence, once the risks are mitigated, right, that time the design becomes robust. Ensuring testability. Latches, if undetected, can interfere with test patterns and scan chain configuration, make it difficult to test the chip for manufacturing defects. Detecting and managing latches improve the test coverage and quality. This is very, very, very important because the early fault detection is needed, because once the chip is fabricated in the wafer, there we can do nothing after the fabrication. That means it is freezed. So anything and everything has to be done before the GDS is getting shipped to the fabrication unit like TSMC or Global Foundry or UMC like that. And by the way, in case you are not familiar about the entire VLSI system and the different companies, how they operate, we have an episode on the VLSI ecosystem, and that was the very first episode of this channel. So you can browse the channel videos and sort as per the release, that means as per the timeline, and you can reach up to this particular episode. In VLSI design, latches are indispensable for achieving efficient data storage, power optimization, and high-speed performance. While they require careful handling to prevent timing issues, their ability to reduce clock overhead and improve data flow makes them a valuable component in modern integrated circuits. When used correctly, latches contribute to the overall efficiency and reliability of the VLSI systems. So here we are done discussing about the cruciality of the latches in entire VLSI system throughout the 3 slides we have just gone through. So let's move on to the next slide. Here in this slide we will talk about the methods for latch detection, and this is very, very crucial. Whether you are in analog design or you are in a digital design, this latch detection is very important, as we have discussed the importance and risks associated with a latch, intended or unintended to be there. Latch detection involves using tools and methodologies to identify level-sensitive storage elements, and this can include RTL linting tool to flag unintentional latch instantiations in register transfer level code. So we can have linting tools. In our channel, we have already a linter of the tickle. And the similar way, each and every language that is used in front-end or back-end, they have an associated linter. So such linting tools can be used to detect unintentional latches, and these are specifically the linters that can parse the SystemVerilog code. Static timing analysis. This is another type of analysis to detect the timing paths and involving latches. Now again, I am emphasizing in our channel we have an entire playlist on the static timing analysis, which is clubbed into 4 different marathon episodes by categorizing the theoretical, the file associated, the additional questions and answers, and the practical application through the open timer. So 4 marathon episodes are now in our channel. You can find them using the marathon playlist, or you can go to the static timing analysis playlist as you wish. Simulation based checks to observe functional anomalies related to latch behavior. So these are based with the simulation tools. By identifying and properly handling latches in VLSI circuit, that means we are detecting whether it is needed or not needed, whether it is there by accident or it is actually needed and it is there. So all this sort of thing. Designers can ensure high performance, reliability and manufacturability of the integrated circuit. Effective latch detection methods help ensure design reliability by identifying unintended latches that can cause functional errors or timing issues. Techniques like static timing analysis, formal verification and linting tools enable designers to catch and correct these issues early in the design process. By integrating these methods into verification workflows, engineers can improve their circuit performance, enhance design predictability, and maintain overall system integrity. So we're done with this particular slide. Now we'll move on to the next slide. Compilers play a crucial and critical role in ensuring correct hardware behavior. especially when handling constructs like always latch in SystemVerilog. This specialized block explicitly indicates that a latch is intended, allowing synthesis tools to check for consistency between design intent and implementation. By enforcing stricter rules, compilers help detect potential issues early, ensuring that unintended combinational logic does not replace a latch and that incomplete conditions do not prevent proper latch synthesis. Now here goes our example without the always latch. So here you can see there is a always block and there is a wildcard entry here, and there is if condition with enable q equal to d. Now this latch inferred as there is no else. So missing else is causing a latch. This could lead to unintended latch inference if the designer forgets an else statement. So this is a mistake by the designer and it will infer a latch. That means it will create a latch in the synthesis level. And I would like to mention here about the synthesis. We already have a series on synthesis using the EOSys open source synthesis tool, and we also have a marathon episode clubbing all the episodes of synthesis using the EOSys tool. So in case you want to explore the synthesis, go ahead and watch either the playlist from the playlist page or the marathon episode of the synthesis. Now again we will see another example here. It is with always latch. That means now we are using the always latch construct. Here we mentioned the always latch and there is if q equal to d. Latch is explicitly expected here. So here it was getting created implicitly and here it is created explicitly. If no latch condition exists, there is no incomplete condition, the compiler will throw an error signaling incorrect use of always latch. So that means it will scan the entire code and see whether a latch is expected here or not. If not, it will throw an error. Compiler behavior. If the always latch is used but the design synthesizes combinational logic instead of a latch, that is a mistake, right? An error or warning will be flagged by this always latch construct. So this is why this is a more sophisticated tool than the general always that is used in Verilog. If a latch is expected but cannot be synthesized due to missing condition, this is also flagged. That means when you intend to create a latch, anything and everything that is obstructing it to get created will be flagged by this always latch construct. By flagging errors or warnings when always latch is missed, compilers enhance design, reliability, and maintainability. These checks prevent unintended behavior, reduce debugging efforts, and ensure that the synthesized hardware accurately reflects the designer's intent. Ultimately, compiler-driven verification helps create more predictable and robust digital designs. We are done discussing about this particular slide, so let's move on to the next slide. Here in this slide, we will talk about the verification aspect of always latch. That means we are finally coming to the HDVL zone, that is the hardware description and verification of always latch. We will be discussing this topic in this slide as well as upcoming next slide. So let's begin. In traditional Verilog, unintended latches often emerge due to incomplete specification or mismatches between simulation and synthesis tools, leading to functional discrepancies. SystemVerilog's always latch helps to resolve this by explicitly defining latch behavior, ensuring that both simulation and synthesis tools correctly interpret the design. By verifying that a block synthesizes as a latch with all necessary conditions, tool can catch potential mismatches earlier, reducing debugging complexity. This explicit modeling is not only enhances design predictability but also aids verification teams in checking latch-specific properties like setup and hold times, ensuring stability and correctness in the final hardware implementation. In traditional Verilog, unintended latches often arise from incomplete specification, mismatch tools, that is simulation versus synthesis. This can be leading to mismatches between functional simulation and the actual hardware, that is the synthesized hardware. Always latch ensures that the tool expects latches during both simulation and synthesis phases, reducing discrepancies. Tools can verify whether a block truly synthesizes as latch by checking conditions and ensuring they match the designer's intent. Any mismatch between design intent and synthesis can be flagged for correction. Explicit latch modeling makes it easier for verification teams to identify and debug issues specific to latch-based logics. Now, whether a latch is intended or not intended, that cannot be concluded by looking into the code. Now, if we have a always latch, that means we are intending a latch to be there. And if it is not there, we will have to debug. So this is the point that we are making here. Verification tools can analyze whether always latch block has all required conditions to synthesize correctly. Missing condition will trigger errors or warnings and enabling early debugging. So that means we don't have to go long steps and then come back for error mitigation. We can do it well ahead with the always latch. Latches often have specific properties of timing requirements that needed to be verified, that is the setup and hold time, stability of output when not enabled. So these are the properties of latches that you can expect in VLSI. Now let us list up some more points in the next slide. With always latch, assertions can directly target the intended latch behavior, streamlining the verification process. Many static analysis tools like Lean tools can identify issues with always latch blocks early, such as unreachable code, incomplete condition checking leading to unintended behavior, mismatched design intent between latch and combinational logic. Verification teams can focus on collecting coverage specifically for latch-based logic. Code coverage tools can identify missing tests for all input conditions, that is enable and D states in the latch. By explicitly specifying latch-based behavior, always latch aids in standardizing designs across teams. Verification environments can include check that enforce use of always latch for any latch-related logic, ensuring consistent verification strategies. The introduction of always latch in SystemVerilog significantly enhances verification efficiency by making latch behavior explicit and predictable at the same time. Assertions and static analysis tools can detect potential issues early, such as unreachable code or incomplete conditions, reducing debugging time. Verification teams can focus on targeted coverage for latch-based logic, ensuring all input conditions are tested. Additionally, enforcing always latch as standard practice helps maintain design consistency across teams, streamlining verification strategies, and improving overall design reliability. So that's all with this particular slide. Now let's move on to the next slide. Here, in this slide as well as the upcoming two slides, we'll compare side by side always FF, always COM and always latch. Always latch we have learned in today's episode, and always FF and always COM we have learned in the last episode. SystemVerilog introduces three specialized procedural blocks: always FF, always COM and always latch, to eliminate ambiguities in the hardware description and improve design clarity. Unlike traditional Verilog always blocks, which could model different types of logic inconsistently across tools, these constructs explicitly define sequential, combinational, and latch-based behavior. By enforcing strict synthesis and simulation rules, they help designers prevent unintended logic inference, improve verification accuracy, and maintain a clear separation between different types of hardware elements. Understanding their differences is crucial for writing predictable and error-free SystemVerilog code. Now let us start the table. Here is our comparison. Always FF models edge-triggered sequential logic, that is flip-flop. Always COM models the combinational logic with complete sensitivity. And the always latch models level-sensitive latch behavior. Now you can see three things are segmented, or you can say they are partitioned away from each other. That means the flip-flop, the combination logic and the latch, they will exist separately in separate buckets of the constructs in SystemVerilog. Clear intent for clocked logic ensures correctness. This always COM clearly specifies combinational intent, reducing ambiguity. And always latch explicitly indicates intent to synthesize latches. So these are very straightforward things. Here, this construct make it much more explicit than Verilog's always block, which was much more implicit, and all the headache goes to the synthesis tool. And the designer will also have the simultaneous headache. It is very easy to understand. Flags error if multiple clocks or resets are detected. Always flags errors for incomplete sensitivity list. And always latch flags errors for missing conditions and needed for an infer latch. Here you can also see that three things are well separated and they have a very targeted nature to do or to debug things. Always FF aligns with simulation synthesis for age-sensitive logic. Always prevents unintended latch inference due to sensitivity issues. And always latch aligns simulation with synthesis for latch-based behavior. These are very straightforward. Moving to the next point, the always FF detects the improper use of multiple clock domains, whereas the always identifies missing combinational inputs or sensitivity errors. Always latch identifies missing conditions for latch behavior. We are done here. Let's move on to the next slide for more points of comparison. Always FF verifies sequential behavior like timing relationships, that is setup or hold checks, whereas the always verifies the logical consistency for combinational outputs. At the same time, always latch validates the latch's hold data correctly in all the scenarios. In the next point, always FF focuses on edge-based transitions for coverage. That means it will work on the clock edges, right? Whether it is rising or whether it is falling. Always ensures all input combinations are tested for coverage. At the same time, always latch ensures conditions triggered latch's behavior are exercised. Always FF debugs sequential issues, that is incorrect flip-flop behavior. Always debugs combinational logic errors such as unexpected outputs. Always latch debugs latch specific issues such as unintended value retention. So this point was for debugging respective to the HDVL. Always FF well supported by linked simulation and synthesis tools. Always supported for static and dynamic checks for combinational paths. Always latch enables latch specific verification in tools. So now we are moving to the verification points we are discussed in this table. Now let's see the final points of comparison in the next slide. Always FF errors occur if no clock or reset is provided or multiple clock exist. Similarly, for always error occurs if incomplete sensitivity list leads to missed updates. Similarly, for the always latch, errors occur if the conditions do not properly infer a latch. That means these are highly targeted and they will flag a definite error if their intentions are not met by the entire coding. Clocked state machines, counters and register are taken care by the always FF. Whereas the always takes care of the pure combinational circuits like adders, decoders, etc. And the always latch takes care of latches, gated data and retention circuits. So thus we have compared the three new constructs in SystemVerilog, that is always FF, always and always latch. By using always FF, always and always latch appropriately, designers can ensure that their intent is clearly conveyed to both synthesis and verification tools. Always FF strictly models flip-flops, always guarantees proper combinational logic behavior, and always latch explicitly defines level-sensitive storage elements. These constructs help prevent unintended behavior, improve simulation synthesis consistency, and enhance overall design readability. Adopting them best practices leads to more robust and maintainable digital design in SystemVerilog. Finally, we have three mutually exclusive constructs from SystemVerilog for three different purposes with no overlap to each other. So that's all our achievement with the three constructs, always FF, always and always latch. So you're done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.